Hi everybody, we now go to section 8.4 in Calculus 2. So in this section, we'll do trigonometric substitution. It is kind of a substitution. However, when we have these three forms, a constant square minus x squared, a constant square plus x squared, or x squared minus a constant square, when we have those three, one of those three cases, then we'll make a trig substitution, meaning that we're going to choose x to be sine, tangent, or secant, corresponding to those three forms. Right. So again, just kind of like the last section, this set of rules, if we stick straight, it's straightforward. We just stick to the rules. So now, if we let a equal to, if we have a squared minus x squared in an integral, then we'll let x equal to a sine theta, and theta have to be in this. So it will have an inverse, pretty much. So when we have a squared minus x squared, a squared minus x squared, since x is a sine theta, substitute in here we have a squared minus a squared sine squared, and then we factor it out and we have that. When we go to an example, then we'll do this in a few more steps. But for now, so if we have constant square minus x squared, this is a substitution. If we have a constant square plus x squared, this is a substitution. And if we have x squared minus a squared, this is the substitution. So, like I said, these three rules are very clear. Just stick to it. There should not be any problem. That concept. The execution, the integration could be a little more complicated. Depends on what we get. Right. So let's look at the first example here. We have 25 squared minus x squared. We have a constant square minus x squared. So this is going to be this. But I will write 25 as 5 squared. So it will look like the form we have here. And let that equal to the integral I. Now, because it is in this form, we're going to let x equal to that. Right? So, let x equal to a sine theta will be 5 sine theta. Right? And then just like every substitution problem, we check derivative and then we solve for dx. So for dx, so derivative dx over d theta, derivative of sine is cosine, and then we move the d theta. And that will substitute into dx. So there's nothing new here. Right. Next, what we have is 5 squared minus x squared. I'm going to solve for that and see what do we have. And of course, when we do that, it will end up being this one. Right. Let's start with 5 squared minus x squared. 5 squared minus x squared. X is 5 sine theta. So we'll have 5 squared of, and then the square go to 5 and goes to the sine theta. Right. Factor out the 5 squared. And 1 minus sine square is cosine square. Okay. And of course, that's exactly what we have here. But I just write a few more details. And of course, 1 minus sine squared cosine squared, because sine squared plus cosine squared is 1. Right. Now we substitute back into the integral. Phi squared minus x squared, that is 5 squared cosine squared. And then the dx is the 5 cosine theta d theta. And here a subtle thing though. When we let the substitution, we assume that theta has to be between negative pi over 2 to pi over 2. So in that case, when theta in this interval, it is going to be positive. Because it's positive, we can take the square root of it. I mean, the square root of a positive number will be itself. I'm going to write that in a minute, but the square root cancel the square in this case. And 5, and so that would be 25 cosine square. Right. So let me write this first. So in general, when we have square root of a square, it's going to be absolute values of a. So if it is in the negative pi over 2 to pi over 2, never mind, that could be potentially be negative. So just keep that in mind, that in general, absolute values, square root of a square is absolute values. So if if theta is between negative pi over 2 to 0, this could be negative, but the cosine is going to be positive, right? So let's write this out. So when we make this substitution, we assume that it is in quadrant 4 and quadrant 1 for that. Now, the cosine for quadrant 4 and quadrant 1 is positive, so that's why this is positive for sure, right? So once again, when cosine of theta, if theta is in this interval, is positive, is greater than or equal to 0, I should say, is non-negative. Right. So if theta is in this interval, meaning here, and cosine for that interval is going to be non-negative, so could be positive, could be 0, but it cannot be negative, right? So, and then we make this substitution, and then we substitute in for the x, substitute for that, and we have this. Now the reason it is positive, the cosine is positive, so when we have the square root, we cancel with the square when it's positive. So every little things there make this work, right? So square root undo the square here, get that back to 5 and get that back to cosine, right? So that's what we have. Right. Now 25 cosine square, we did this on the previous section. Whenever we see this, that is the power reducing. For this, when we have cosine square, and cosine square is 1 plus cosine of 2 theta I mean 2a over 2, and we're going to apply that into cosine theta. Right. So with that, the integral equal to 25, and the cosine square here using with power reducing identity, we have 1 plus cosine of 2 theta divided by 2 d theta. Right. Now, the 25 and the 2 are constant. We'll take them outside of the integral. So 25 over 2. Or 1 plus cosine of 2 theta d theta. Now the integral of this will be easy. We still have 25 over 2. Integral of 1 is theta, and integral of cosine 2 theta is 1/2 sine of 2 theta. Right. Right. Now, of course, the plus a constant c. That is correct. However, I remember the question originally we have x, so we have to write this in terms of x. So now we have to go back to the previous, to this. Now, if x is equal to 5 sine theta, then obviously we can solve for sine theta, right? So from that we can say sine theta equal to x over 5. And if we want to solve for theta, keep some space here. So theta equal to sine inverse of x over 5. Right, so that's good. We can substitute that into theta, which is good. Now what is the sine of 2 theta? Now that is another trick identity. The double angle, that is sine of 2a is equal to sine a cosine a. So sine, and we're going to substitute this into sine of 2 theta. $25 and theta plus 1/2, and then we have substitute that in here. 1/2 and 2 cancel out. So this is 25 over 2. Theta plus sine theta cosine theta plus c. Now, we know sine theta is x over 5. And theta is the sine inverse. Yeah. So theta is the sine inverse of x over 5. Sine theta is x over 5. Just need to solve for cosine. So that requires a right triangle. Angle of theta. Sine is opposite over hypotenuse. So the opposite is x, hypotenuse is 5, equation will be 5 squared minus x squared. And in that case, cosine of theta will be equal to equation over hypotenuse. Equation over hypotenuse square. So that actually is just 5, sorry. So just that. Right? Now, we substitute back everything back into here. We will have 25 over 2 and then theta is equal to sine inverse. And the sine theta is x over 5 and cosine theta is square root of 5 squared minus x squared over 5 plus c. Sorry. Yeah, so that's what we have. Right. And then if we want to, we can multiply it out. So 25 over 2 sine inverse of x over 5 and 5 times 5, 25, cancel with this 25, it's plus 1/2 x is 5 squared minus x squared plus c. Right, so that's what we have. Right. Now the nice thing about this is this formula is used to find the area. Just want to write a little note here. So when we have a circle at x squared plus y squared equal to a squared, if we want to find the volume, the area of this one, is going to be equal to this segment times 4, right? So it will be 4 times the integral 1 from 0 And if x squared plus a squared equal to a squared, so this gives us y equal to plus or minus square root of a squared minus x squared. And we're going to choose positive because the first one is positive. Sorry. And it goes from 0 to a. This is not Cal 3, so I'm not going to do that. From the a. And then we have a squared minus x squared dx. And we use what we just have and we can integrate. And this will show that the area of the whole disk is going to be pi r squared. Right. So the area of the whole disk is 4 times a quadrant, a quarter of a circle multiplied by 4, and that's what we have. Right. So the area of the whole disk is equal to that. Right. Next, we're going to solve this one. Right. Before we do anything, I will write this and move the dx to the back. 16 minus x squared to the 3/2. 16 is 4 squared. Move dx to the back. Now with this, we have a constant square minus x squared. So the substitution is x equal to a equal to sine theta, and theta is 4. I mean a is 4. X equal to 4 sine theta. Right, take derivative. For cosine theta, move theta over. And we can substitute into dx. Also, we have 4 squared minus x squared. We can write that into one term. X is 4 sine theta. So 4 squared minus 4 squared sine squared. Factor out the 4 squared. One minus sine squared is cosine squared. Right, and we substitute that in here. So the integral equal to 1 over 4 square cosine square. Actually, let's just write this as 4 cosine theta square. That better. So 4 cosine theta square over 3/2, and then dx is this. Two and two cancel out, so I have 4 cosine theta. 2 and 2 cancel, that raised to the 3rd power, and then for cosine theta d theta. Uh, 4 cubed is 64, and then cosine cube, and then for cosine theta d theta. Cosine cancel, we have 2 square left, so 1 cosine cancel with 1 cosine, so we have cosine square left. 4 on 64, let's take it outside. 4 on the top, 64 on the bottom, so that will be 1 over 16, but just for now. Right, luckily we have something rather simple here. 1 over cosine square is secant square. 4 over 64 is 1 over 16. And then secant square. Integral secant square tangent. Because derivative of tangent is secant square. Right. So we just have that. Simple enough. Now we just need to write down what is tangent. For that, we go back to here. If sine x is 4 sine theta, so we can solve for sine theta is x over 4. Opposite over hypotenuse, the adjacent will be 4 square minus x square. So with that, tangent equal to opposite over adjacent was x over 16 minus x square. So we just have that. So it says 1 over 16 tangent that. I noticed that we cannot simplify anything here, so just leave it like that. Right. So when we have a constant square minus x square, this is the substitution, and after that the integral could be anything, so depends on the problem. It could get very complicated. Right, so that was that. Now we go to the second type of the problem, where we have a constant square plus x square, or x square plus a constant square, either way. Right. Now, first I put the dx on the back. And the 9 right is 3 square. Put the x on the back. Now constant square plus x square, that is tangent a tangent theta 3 tangent theta. Right. Take derivative. Tangent, derivative tangent is secant square. Move the d theta. So that is dx. We can substitute in here for dx. Now the 3 square plus x square, we can rewrite that as one trigonometric expression. x squared is 3 tangent theta. Just x squared first. So give us 3 square and then 3 square tangent square, and then factor out the 3 square. One plus tangent square is secant square, so 3 square secant square, and then we can write that as 3 secant theta square. Right, now that we substitute back into the integral. One 3 square plus x square is going to be this. Three secant theta square and then we square again. The x is that 3 secant square d theta. Right, simplify. 3 square and then square again, so that gives us, just for now, let's write 3 secant theta square and square that to the 4th. And we have that. So 3 to the 4th is 81 secant to the 4th. And then 3 secant square. Take the 3 outside, 81 on the outside. And then we have secant square over secant to the 4th power. Can cancel that. There are 4 of them, cancel 2. We still have 2 of them left. So we have 1 over secant square. Now 1 over secant square is 1 over secant is cosine. So this is going to be cosine square. A over 31 is 1 over 27. And 1 over secant square is cosine square. And similar to one of the problems we did earlier, cosine square, that is the power reducing. Cosine square is 1 plus cosine of double angle divided by 2. And now we write that for cosine square. Right. And of course after that, when we integrate, there will be sine and then we use double angle. So kind of like the first one we did. on this video. So take the 2 outside. So we're at the bottom. And that will be 1 over 54 integral of 1 is theta, integral of cosine 2 theta is 1/2 sine of 2 theta. Let's see. Once again, we have the double angle. Sine of 2 theta equal to sine 2 sine theta cosine theta, and substitute into here. So 1 over 54 1/2 2 sine theta cosine theta let's see, 2 and 2 cancel out, so we have 1 over 54 theta plus sine theta cosine theta. Let me zoom back out so we can see the whole problem. Alright, that's better. Now we need sine theta, and cosine theta. So we go back to the first part of the problem. X equal to 3 tangent theta. So tangent theta is equal to x over 3. It's good. Opposite over adjacent. So this is opposite over adjacent. But not only that, we can say theta is equal to tangent inverse of x over 3. So we have a little triangle, opposite and adjacent. So the hypotenuse is equal to 3 squared plus x squared. With that, we can say sine is opposite over hypotenuse. And cosine is adjacent over hypotenuse. And we substitute those two into here, and of course the theta equal to theta here. So there are 3 things that we need to substitute in. 1, 2, and 3. So that gives us 1 over 54 tangent inverse of x over 3, and then plus sine is x over square root of 3 squared plus x squared, and then 3 over 3 squared, square root of 3 squared plus x squared. That is 1 over 54 tangent inverse 3x on the top, and multiply the bottom. Square root and square root give us a square, so we just have 3 square plus x square plus c. Right, so that's what we have. So usually where we have the cosine square, we use the power reducing, and that's followed by using the double angle. Part of the routine when we see the cosine square. Right, so that's what we have. Now let's zoom back in. So that's pretty typical problem. So method substitution depends. The problem could be very complicated, and up to that. Right, the next problem is also complicated. As you see, I have the whole page for that problem. Right. Oh, let me move. Right, here. Right, so what we have here is x squared plus 1, or 1 square, or constant square. I will write this as square root of, we can say 1 square plus x square. So it will look like this form. So that's the substitution. Right. Now this is kind of classic problem, especially if we use the arc length. I'll find the length of an arc, section 6.5. We will see a lot of this. And when we work that section, we just use a calculator to estimate this integral, because this takes a lot of time to do. Right. Now, okay, let's start. Substitution. A square plus x square, constant square plus x square. So the substitution is, let x equal to 1 tangent of theta, or we just say 1, or just tangent of theta. Right, that's the substitution. We'll take the derivative and show for dx. So dx equal to secant square d theta. So that gives us dx. Now we have 1 square plus x square. We'll write that into one trig function. 1, x is tangent square 1 plus tangent square secant square, which I will write as secant square. Right. Substitute that back in here. So the integral equal to square root of secant square and then dx is secant square d theta. Square root of secant square is secant. Yeah. Yeah, let's actually just put a square right here. that better. Square cancel the square root. Right. Remember, we talked about we could check the quadrant. Tangent, when we make that substitution, has to be in quadrant 4 and quadrant 1, and secant in quadrant 4 and quadrant 1 is positive. So that's why we can cancel out square root and square. Square root undo the square. Right. So we have secant times secant square d theta. Actually, that is the secant cube. Right. A secant cube. This is the classic problem. Actually, we did this before, right? Remember, this is in previous section when we talk about secant cube. And for the secant cube, to recap, we're going to write like this and use iteration by parts. Let's find that problem. Right, secant cube. This is in section 8.3, page 37 in the note. Secant cube, we write like that, iteration by parts. After a few steps, we'll get to this is the integral. So I'm going to write out the formula. That's something very important. So from section 8.3, example 3D2. So from that, we have secant integral of secant cube is 1/2 secant tangent plus ln secant tangent, secant plus tangent, plus constant c. Right. So that's what we have from the previous section. And with that, we can write secant cube. So the integral will continue. And it equal to 1/2 secant tangent plus ln of secant plus tangent. So just need to determine what is secant, what is tangent. So we'll go back to this. Tangent is equal to x, so we can say tangent equal to x over 1. But if we want tangent, if we want theta, it will be tangent inverse of x, right? So x equal tangent, so theta equal to tangent inverse of x. Now we just need to find secant. Actually, we can just say secant square is equal to 1 plus tangent square, and we can solve for that way as well. But tangent is opposite over adjacent. So the hypotenuse is 1 plus x squared, 1 square plus x squared, or 1 plus x squared. And then secant is reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Hypotenuse over adjacent, or just 1 plus x squared. And substitute into here, so we have secant and tangent. So that gives us 1/2 secant. What is secant? Oh, that. Tangent. Oh, we don't even need this. Tangent is equal to x. Ln secant and tangent is x. And so let's just put x in front. So this is a classic problem of square of x squared plus 1 or plus a constant square. We see this a lot in the length of a curve. I zoom out so we see the whole problem. So the substitution is because it is x squared plus a constant square or constant square plus x squared, the substitution is using the tangent. And when we do that, we have the substitution. This is pretty standard. It turned out to be a secant cube though, which will take a lot of time, but previous section we proved that this is the result. So we just apply that, and that's what we have. Right, so that case number 2, where we have a constant square plus x squared. Now we just need to do one example for case number 3, where we have x squared minus a constant square. Let's do it back in. So again, 3 cases: constant square minus x squared, constant square plus x squared. Of course, when we write like this, we can also write x squared plus a squared. So the sum of x squared plus constant square, we're going to use tangent. And if we have x squared minus a squared, x squared minus constant square, that is the secant. Like I said, the rules here are very standard or straightforward. Just apply that. Depends on the problem. It could get very complicated, but at least we know where we start. Right. So that's good. I just want to write. It looks silly, but here we just have x squared minus 1 square. Looks silly, but this is in the right form. So the substitution here is secant. One secant or just secant. We'll take the derivative. Oops, forgot the dx. Right. Take the derivative and solve for dx. Derivative of secant is secant tangent. Move the d theta. and that is the dx. After that, we need square root of x squared minus 1 square, particular x squared minus 1, wrong color, x squared minus 1 square, x squared x is secant so secant square minus 1 is tangent square. Let's write that as tangent square and substitute into here. So the integral equal to 1 over x. We did let x equal to secant and then we have the square root x squared minus 1 square, that is tangent square, and dx is going to be secant x secant tangent square root of tangent square, that cancel out. We have secant tangent and then secant tangent. Alright. Actually, it works out perfectly and cancel everything. We just have d theta. So integral of that is just theta plus c. So, and we don't even need a triangle for this problem because x equals secant theta, so theta equal to secant inverse of x. And we substitute that in here. Yeah. So that's what we have. And like I said, in this section there are only 3 cases, and we just follow that exactly as is. Sometimes it works out nicely and we don't have to do much. Sometimes that is very complicated. That depends on the what integral we have after that. So, and usually when we have the square root, then this will come in handy. Not only square root, sometimes we have like 2, 3 half power. So bottom line is we have a constant square and then x square depends on the combination. Then we use the equivalent substitution. And like I said, we just have to stick to the rule here. And then after that, we just integrate trigonometry integral. So after that, we just have a trig function. You could get like secant cube, which is a bit more complicated, or sometimes it turns out it cancels everything and we don't even need to draw a triangle. But other than that, the integration could be complicated after the trig substitution. But the focus here is of course the trig substitution, and there are only 3 scenarios that we can use. Right. With that, I finished section 8.4, and as always, thank you for watching.